Good morning. Thank you all for your presentations. This is exciting work. I have a question. I kind of want to circle us back, Peter, to how you were framing the discussion today around innovation intersecting with sustainability. I'm curious what thoughts you have as far as where we are and what our limitations are that are keeping us from taking the lessons of biomimicry, but innovating with new material solutions that still might be problematic from a material science standpoint. Is bioutilization really the only way to kind of avoid creating new problems from a material science standpoint, or what are the limitations? Certainly you talked about testing requirements as a significant one, but I kind of wonder what your perspectives are as far as like where we are in making progress towards more sustainable material solutions that also include biomimetic methods, and what those limits are that we kind of need to overcome in order to have more success in that arena.
That's not for me. That's for the people working on this problem.
Maybe I can start with it. So I think you heard several things over the last 2 days about how and where the pitfalls are. One thing that my perspective has been is that sometimes when we look at the biological structures, we find certain characteristic which makes them work the way they work. However, to reproduce some of these things and exactly replicate the mechanism behind it takes time. And the time and then the structure, the length scale of the structure typically is in the range from 10 to 100 nanometers, seems to resonate across many other examples that we see in nature. And our fabrication tools are very limited in that range. We either have very expensive ways of making that from 10 to 100 nanometers, or we find things which are just so intricate that we don't have the capabilities to do these things even. Nature does it in a very unique way. It does self-assembly. It does all of these things with a bottom-down control of molecules, which are so precise, proteins and other biological systems. So I think the challenge has always been for me, at least the kind of things that I've looked at, is how to do it in a cost-effective way and still manage to reproduce what nature does.
I think there's maybe something else to consider as the end-of-life fate. Nature or biology is fantastic in that, and in material science and engineering. We have to be very careful when we're looking into very complex composite surfaces. And as Anna presented, if something erodes within a couple of seconds and there's like a million different molecules, elements in there, if it's an outdoor application, that ends up in our groundwater. So, I think it's something where we need to be very conscious of using high tech, using specific combinations of materials, but not forgetting that one day, these applications will either be landfill just because, that airplane, that wind turbine is 30 years old and not being used anymore, or abrading along the way and might not be cut back down into its constituents. And it's not biodegradable, most often, what we do.
Yeah, I agree with both these points. The only thing I will add is cost in another sense, right? So for most of the applications that we're looking at, there are existing solutions that can work, right? So let's say if I had to shed ice from an airplane, I know there are heaters and boots that currently exist. So unless you're offering something that is far better at much lower costs, it's very hard to transition things that are in the lab, even in startups, to actual applications. And so unless we offer some of these things at really, really low costs, many times these things for different applications, we've been quoted, it can't be more than a few cents a square foot, right? And so when you're trying to translate things that are, cutting edge technology to 5 cents a square foot, that sets a limit for actually what can actually be translated. And so I think the more time goes on, we kind of keep coming up with better and better approaches to hopefully get to that point, and that just takes a bit of time. So once you've understood the physics, to actually translate that into something that will be applied outside while figuring out the cost is probably, to me, has been the biggest limitation in this space.
Then
Just curious, with your testing, have you investigated anything at very, very low temperatures like 50 Kelvin, which is, of course, in permanently shadowed regions on the moon, which we're just slightly interested in?
I can answer. Yes. So we've not gone to minus 50 Kelvin for one of the other, not this particular agency, for one of the other private companies, I should say. They were very interested in some of this. And so we could test down to minus 100. We didn't have minus 100 C. We didn't have capabilities of going beyond that. There are things that I know are unlikely to work between, at least most of the things that we've made are unlikely to work below maybe minus 120 to minus 150 C. Potentially there's a way of going beyond that, but given, like, certainly we couldn't test any of that in our testing facility. But up till minus 100, we've been able to do so.
Pick me up in the middle and then down in front and so around the side.
I'm struck by the fact of how we're talking about biomimicry. A lot of the things that you're talking about are these sort of industrial products, which are like a boat or a plane or a turbine, which are inanimate. And I really feel like there's something interesting in questioning how, rather than just coating or making a different surface or some other kind of thing on an inanimate object, that you don't create some way to make the object more animate. So if you're having a plane or something, there's not some mechanism whereby there's like a muscular bat sort of flexing or like a fish sort of tail moving. And where is that sort of in your mind, in the biomimetic future of having these things be less like us crawling out of the industrial age and more into the Biocene of animate things?
What the example of something vibrating or so on airplanes, that's one of the methodologies that's presently used. Problem is, it's very energy intensive. So there's a trade-off between trying to move things or imitate motion and aspects that animals use on an inanimate object, be it a wind turbine, be it whatever it is, where to actuate that motion, we need, again, energy. So there's a very, and I guess comes along with your question from earlier on, there's a very fine line between trying to imitate very truthfully what nature is doing, but not being able to do so intrinsically, but needing, again, that energy, those chemicals, whatever it is, externally. And I think, definitely can speak for that field, that I think it's something that we have in mind, but it comes along with what Anish mentioned earlier on. There needs to be a benefit on the cost side. Yeah, there's probably at some point we're getting into that realm of a paradigm change, and it comes with political commitment to certain goals. And suddenly it doesn't matter, in parentheses, how much something costs if it gets us closer to the goal, because if a certain industry doesn't get close to the goal, they have to pay huge penalties. At that point, something along those lines can become more interesting. I think where it is right now, and if we're truly just competing in the economical sense with what is out there, it becomes very difficult.
But if it happens, it'll happen in Montreal.
Just to add to it, because you brought this up as a question, it's an interesting historical fact as well, that the solution that was developed when the aircraft had these problems early on, it was in Akron, Ohio, that it came up with this rubber balloon, which is mechanical, which is very simple, and all it does is essentially blows air into this rubber tube, and that expansion of the rubber just breaks the ice. And so that was B.F. Goodrich, which was located in Akron, which came up and it's been still used.
Yeah. I can add maybe one more context to that, and so kind of building off of what's already been said, it's possible, and that some of the work going on in the lab right now is actually where I'm not using the boot over the entire area. Can you actually design surfaces that there are specific locations where you might be using some sort of a motion that kind of helps it for the entire thing? So you can actually design things to be much more energy efficient and smart in being able to tell exactly where the pressure points are going to be, and that's how you kind of design things. So it is that is actual work being done right now.
So, as a transdisciplinarian, sorry, am I next?
Just next question is up on the wall.
As a transdisciplinarian, I'm interested in exploring boundaries. And what I love about this meeting in terms of the big picture is how we have art and science juxtaposed. And I don't get to talk to material scientists very often, so here's my question. There's a whole field now called neo or new materialism, where the separations between mind and matter are being considered in new ways. I mean, quantum levels being one perfect example. So do you think that the material engineers are thinking about materials in new and different ways in this evolving consciousness that we have as a species?
So I was thinking about the question while you were saying this, is how to interpret, and there are many ways to think about it. So the first question that we are right now really struggling with is plastics. Let's take that as an example. We've been designing plastics for hundreds of years to solve all kinds of problems, even medical problems. And the challenge that we are facing right now is sustainability. The way we were thinking when we were designing materials, that they should last hundreds of years. That's the way we would justify that this plastic we made is so durable, it's strong, it would last long time. And now we have to rethink that whole idea and think about how it actually would disappear after a certain period of time. So now the materials community is thinking materials in a very different way than they were thinking 100 years ago, where the benchmark was not just about strength and last as long as possible, but to really design materials which will function and then disappear. And how to do that well, and so they don't disappear early, they don't disappear when you're really sitting on the chair and it falls apart. That would be terrible. So that has been really the mindset right now for us, at least in the materials world, is how to think a little bit more differently than what we used to do that some times ago.
I can add a little bit. Yeah, so being part of the material science and engineering department, right, at Michigan, I get to see sort of how all of this is evolving. There has been a huge shift in sort of the designing of materials over the last 10 years, particularly as computation has picked up, right? So there used to be a lot of work that experimentalists like myself would be doing, and simulation guys would be doing something else, and they could never quite reach the length scales that we would be interested in, but they would find something interesting that we could never explore with our tools. I think both of them are converging now. So the simulation part has really evolved. They're able to sort of simulate larger and larger length scales. They're able to utilize techniques. There's this whole initiative, so-called as the Materials Genome Project. So just like the regular genome project, right? So you're kind of really working on designing things from the ground up, completely new properties of materials. On the other hand, on the experimental side, there's now all these new experimental tools that have been developed to be able to actually validate the predictions that the simulation folks had been making, and we could never get to those length scales before. So I think there's a lot more convergence happening, and that's where I think the best chances for just rapid progress and just completely disruptive science lies as these things come together. For the longest time, simulation guys would produce something which would have no relevance to what we were doing, and vice versa. But I think now because of the convergence, this is changing.
I'd like to get Andy, but I also have, there were two questions up there that, yeah. And then we'll come back to Andy. Thank you. Yes. We've got time. We'll get you. Okay. I promise.
Thanks. I wondered if you could talk a bit more about this relationship or lack of relationship between isophobicity and hydrophobicity. To me, that's very counterintuitive, because is it the case that everything that's isophobic is also hydrophobic, but not everything that's hydrophobic is isophobic? Or could you talk about?
Typically, when we talk about super hydrophobicity, we talk about air trapping surfaces. And I use my hand as an example. So we have our liquid interface on the top of some pillars, and then we have some cavities that are air-filled. And then we saw earlier on the pitcher plant, In that case, it would be lubricant filled and we have another surface on top. The problem is when we move into cold climates or colder situations, surface tension changes. And then also when we're in real situations like I was alluding to earlier on, where we have drops that are impacting at high speed onto a surface, the pressure is just so high that these little air pockets, they collapse. Now, it depends on what the surface looks like. If it's closed cavities, when the air has to dissolve in the liquid, otherwise it's not collapsing. If it's an open network, then the air is just being pressed outside. But sooner or later in those situations, those pockets might collapse, or if they don't collapse entirely, they get compressed. So if you have ice, now frozen, it's my other hand, sitting on top there, you get into an interlocking situation. So in that moment, when there's a force being applied to that super hydrophobic surface that was super water repellent, it's now not necessarily ice repellent, because if it was a smooth surface like the one that I was showing us, well then the ice can just delaminate. If I have a surface that is rough and I needed the roughness to be super hydrophobic, now I get these interlocking asperities, and now they are getting sheared. So at that point, I need to fracture either the ice or the solid or both, depending on the material properties of the respective. So typically, those super hydrophobic surfaces that are based on air trapping don't work too well under a wide range of icing conditions. They might work for very specific lab situations under very specific temperatures, very specific freezing regimes, but they don't work under a broad band, and which we typically need for the industrial applications. So this is where there's the little disconnect, and where's why I guess we've turned somewhere else, because the super hydrophobicity doesn't mean necessarily super ice phobicity or ice shedding ability.
Just want to add a different context to it. So we heard two mechanisms. We heard mechanism that you can reduce the adhesion, and Anish just started touching up on the last slide, where you can actually lower the nucleation rates, and that way you can stop ice from actually forming. So that would be another interesting strategy. There are two big, broad strategies. The second strategy, actually, where hydrophobicity may have an important role. And surfaces that have been made hydrophobic, not super hydrophobic, just the chemistry of the surfaces, they tend to nucleate slower than if you had an hydrophilic surfaces. So there has been some studies that have outlined that if you do fluorinated surfaces and things like that, you could lower the nucleation rate. That's interesting option to consider, but of course we have to think about all the practical limitations, again, back to coatings and whether they'll be resilient to impact and all that stuff. But at least there is some chance of going in the other direction.
Smooth surface.
There are smooth surfaces, yeah, but chemically altered.
Andy.
I'm up?
Yes.
Okay. So I think that there's some really interesting irony in your presentations, in that you were looking at nature and trying to be inspired by nature as to how nature dealt with preventing ice formation on different surfaces. At the same time, you showed a tree that had formed ice on it and fell and was a complete failure of being able to prevent ice formation. So in both cases, nature succeeded and failed.
That's the thing. We have to go beyond what nature's been able to achieve. It's in many different fields. Like we were kind of looking at surface wettability for a while, right? Earlier on, Peter kind of showed the lotus leaf and so on, right? So my postdoc work, for example, was making super hydrophobic surfaces, but also oleophobic surface. So if I take a drop of oil, for example, on the lotus leaf, the same lotus leaf which is repelling all these water droplets gets completely easily wet by oil. It's the same thing as if you take your non-stick cooking pan, right? You take your Teflon coated pan, you put a drop of water on it, it's hydrophobic. You put cooking oil, vegetable oil on it, it will spread because oils have a much lower surface tension. So in many cases, yes, nature does great in certain situations because it's evolved to be able to address its environment. it doesn't work for the entirety of the range that we may be interested in an application, right? I want my suit to be able to repel wine also. When it falls on it, it should bounce off, right? I don't want to stain on it. The lotus leaf doesn't care for it. It's not coming in contact with wines, but we are. So the application range is kind of different, and so you kind of have to develop it based on the environment.
Just to be fair, the tree was founded by Sidewalk and Road, and I'm pretty sure that it was struggling just to, get a break. But anyhow.
The wrong tree.
Yeah.
We're going to thank these guys. Thank you very much.